Hello, you are watching Birthday Paradox related problem video, part 2. It occurred to me that one could ask a bunch of other questions in the birthday paradox setup. First, let me introduce a convenient notion of n birthday. If n people in a group of n people share a common birthday, I call that birthday the n birthday. Let me illustrate that definition by an example. Suppose you have a group of people, and some of them have common birthdays. Perhaps those two guys were born on the 2nd of June, and those three people on May 15th. These two share a common birthday as well, say October the 6th. We can condense that information in the statement that June the 2nd is a 2 birthday, May the 15th is a 3 birthday, and October the 6th is a 2 birthday. There are 1 birthdays and 0 birthdays as well. If no one in the group was born on January the 2nd, this day is a 0 birthday. As you can see, there are no 4 birthdays and no n birthdays for m greater than 3. But there are lots of 0 birthdays. If you do the counting, you can convince yourself that we have exactly 1 3 birthday. That is the birthday of the guys painted in blue. 2 2 birthdays. That are the birthdays of the guys painted in red and white. And 3 1 birthdays. There are 359 0 birthdays as well. Now, with the notion of m birthday, I can pose my question. What is the average number of m birthdays in a group of n people? Remember, I want to average over all possible groups of n people. Let me denote the quantity I am looking for, f and m. In order to answer the posed question, that is, to find the average number of m birthdays in a group of n people, I am going to use the unrigorous method I've introduced in the previous video. Let me remind you the unrigorous method. First, take the average group of n-1 people. Second, add a random person to it. Third, compute the probabilities of the average characteristic to stay the same, increase, and decrease. And fourth, use these probabilities to compute the average characteristic for the group of n people. The details can be found in the previous video. The main idea is average group plus random person equals average group. Before I start exploiting this method to answer the posed question, let me state a few properties of f and m numbers. Do you recall the average number of different birthdays, e sub n, I've calculated in the previous video? It is true that e sub n equals the sum of f and m. That means that the average number of different birthdays equals the average number of 1 birthdays plus the average number of 2 birthdays plus etc. up to the average number of n birthdays. And moreover, fn0 equals 365 minus e sub n. That means that the average number of 0 birthdays, or non-birthdays, is 365, the total number of days, minus E sub n, that is the average number of different birthdays. If you plug in the expression for E sub n, you can see that fn0 equals alpha to the nth power over 1 minus alpha. Now I am ready to start. I am going to obtain the recursive relation that connects fnm to the fn-1 m-1 and fn-1 m. Let me start with fn1, that is the average number of days on which one person was born only. If you add a random person to the average group of n-1 people with fn-1 different 1 birthdays, then with the probability fn-1 1 over 365, that person will hit someone's 1 birthday. In this case, the number of 1 birthdays will decrease by 1. Then look, with the probability E sub n-1 minus fn-1 1 over 365, that random person can hit someone's 2 birthday or 3 birthday or n birthday with m greater than 1. In this case, the number of 1 birthdays will stay the same. Finally, the birthday of that random person may be unique in this group of people, and in this case, the number of 1 birthdays will be increased by 1. If we collect all that information, we can get our recursive relation for fn1. After some cancellation and using the definition of alpha, that is 364 over 365, we can get our recursive relation for fn1. We can use that recursive relation to obtain the expression for fn1. It involves the f11 quantity, that is the average number of 1 birthdays in a group that consists of only 1 person. It's obvious that f11 equals 1. So fn1 equals m times alpha to the power n minus 1. We can use the same reasoning to obtain the expressions for fn2 and fn3. You can use the same method to obtain the recursive relation for fnm quantity. That relation contains 4 terms. You can do cancellation as well. Now, to make things simpler, I am going to guess the expression, the final expression for fnm, and I am going to plug it into the recursive relation and prove that it satisfies it. So, here is my guess for fnm. Note that for m equals 0, this expression gives the correct answer for fn0, the average number of 0 birthdays. Next, if m equals 1, the formula gives the right answer as well. fn1 equals n times alpha to the power of n minus 1. For m equals 2, the formula gives the correct answer as well. Now, I am going to plug the guessed formula into the recursive relation. Well, the guessed formula satisfies the recursive relation. So, the guess is verified. We have solved the problem. Here is our hero of the day, the expression for fnm. Yet, we can verify this expression in the other way. We know that E sub n is the sum of f and m's. And moreover, in the previous video, we obtained the analytic expression for E sub m. After a few algebraic manipulations, we reobtain our formula for E sub n. Checked. At the end, I want to show you the graphs of the heroes of this narrative, f and m's and E sub n. I want to thank everyone who has watched my videos so far and has made their way through lengthy formulas and derivations and scary black backgrounds. Please leave your comments or questions, likes and dislikes on YouTube. In the next video, I'm going to abandon the lengthy and tedious derivations, and finally I'm going to show how all that f and m's and E sub n's relate to the Busby paradox and to the cryptographic attack called the Busby attack.